Alright, so this is going to be another pretty long video, I think. We're going to cover 3 sections here, and they're all kind of related. So we'll start with section 10.1, which talks about the circle and the parabola. And I'm sure all of you have heard of both of these before. In fact, we've already talked about parabolas in this class. So let's go ahead and start with the circle. The definition of a circle is that a circle is the set of all points that are the same fixed distance from a fixed point, called the center. And the fixed distance is called the radius. So what we have here is a fixed point here, which is the center of the circle. And we have the set of all points here that are the same distance from that center. And that fixed distance here is what we call r, which stands for the radius. So what we want to do is talk about how do you get the equation for all the points that are on a circle like this. Now, I'm going to call the center of our circle HK. And any point, let's say any point P on the circle, we're going to call that point XY. So to do this, we need to talk about the distance formula. The formula for the distance between any two arbitrary points in a plane is distance equals the square root of subtract the x values and square it, subtract the y values and square it, and add those together, and again, then you take the square root of that. So for our circle here, one of the points is the point P, that's x and y, and the other point is point C, which is h and k. So the distance between these 2 points, you take the x values, which is x and h, subtract those and square it. You take the y values, which are y and k, subtract those and square it, add those together, and then the square root of that whole thing is equal to the distance between those 2 points. And again, we know that distance is what we're calling r, which stands for the radius. So this comes directly from the distance formula. Then what we can do to kind of simplify this equation is we can just square both sides of the equation. And when you square the left side of the equation, it cancels the radical, and we end up getting this. And when you square the right-hand side, we simply get r squared. And so the equation for a circle that has a center at hk and a radius equal to r is this equation right here. And this is the standard form of a circle. Let's do some examples. So in example number 1 here, we want to graph the circle who has this equation. So the first thing we need to do is we need to find the center of the circle. The center of the circle can be obtained by simply looking at these 2 numbers here. Let's go back to our equation real quick. Remember, the equation for a circle is x minus h squared plus y minus k squared equals the radius squared. So if the center has coordinates h and k, what you're looking for in the equation is the opposite of these 2 numbers. So for example, here, the opposite of 3 is negative 3. And the opposite of negative 2 is positive 2. So the center of this circle occurs at the point negative 3, positive 2, which is this point right here. Next, we need the radius of this circle. Now let's keep in mind that 16 here, that's the radius squared. And so if r squared equals 16, I think it's pretty clear that r must be 4. Now to graph the circle, what we do is we go to the center, which is at negative 3, positive 2, And then from that point, we are going to count 4 units up, 4 units down, 4 units to the right, and 4 units to the left. And we'll put points at all of those locations. And again, I'm going 4 units because the radius of the circle is 4 units. And then once we have those 4 points, just sketch the best circle that you can. And it doesn't have to be perfect. My circle here certainly is not perfect. Okay, but this is good enough. Now, for our next example, it's pretty much the same idea. So to graph the circle that is represented by this equation, first of all, we need to find the center of the circle. And so the center for this circle is going to have an x-coordinate of +4. And what's the y-coordinate? Well, we just have y squared. And so you need to keep in mind that y squared is the same as y minus 0 squared. And so the y-coordinate of the center is 0. And then the radius, well, again, we know that r squared equals 30. So that means r will be the square root of 30. And so if we're going to graph this, we need to approximate what is the square root of 30. And the square root of 30, if you plug it into a calculator, is approximately equal to 5.5. So again, to graph this circle, first thing we're going to do is we're going to graph the center of the circle, which is at x equals +4, y equals 0. And then from that point, we will graph 4 points that are 5.5 units away from that center. So again, we use the radius value here. We're going to go 5.5 units up, 5.5 units down, 5.5 units to the right, and 5.5 units to the left. And then we'll just sketch the best circle that we can. And again, if you're doing this online in homework, usually the online programs will have a tool for you to graph your circle, and it's much, much easier to do. So these are the basics of graphing circles. Let's take a look at some other examples. Now, this one here is actually a really simple thing to graph, but sometimes people get complicated when things are overly simplified. So we have x squared plus y squared equals 9. And I just want you to notice that this is the same equation as x minus 0 squared plus y minus 0 squared is equal to 9, which you can actually write as 3 squared. And as soon as you realize this, you can easily identify the center of this circle is 0, 0, and the radius of this circle is equal to 3, right? Because again, this is r squared. R squared is 9, or 3 squared, so r is 3. And then from there, we can simply go to our graph. So the center would be at the origin in this case, and the radius is 3 units. So if we go 3 units to the right, 3 units up, 3 units down, and 3 units to the left, we can sketch the graph of the circle. And again, it doesn't have to be perfect. Okay, that's good enough. All right, so don't let a simple equation fool you. Simple equations are nice. In fact, when you have x squared plus y squared with no other x's or y's, what that means is that the center is at the origin. All right, so for our last problem, we're going to find the center and radius of the circle represented by this equation. Now that at first, this should look a little strange because this equation looks different than the other equations. And what we're looking at now is what we call the general form of a circle. So when you have it written in this form, x minus h squared plus y minus k squared equals r squared, this is often called the standard form of the circle. And the standard form is the form that we like, because when it's in standard form, it's easy to see the center is at hk and r is equal to the radius. when it's in general form, you can't easily identify the center or the radius. So what we need to do here is we need to put this into standard form. So how do we take this equation and make it look like this? How do we do that? Well, if you guessed complete the square, you're absolutely right. So what we need to do here is complete the square on this equation. So let me rewrite the equation. First of all, let me write x squared, and then we have minus 6x. I'm going to write that term next. And I'm going to leave a little space here because we're going to have to complete the square on that. And then I'll write positive y squared next and positive 4y. So that is these two terms. And then the plus 4, I'm going to move that to the other side by simply subtracting 4 from both sides. And that's going to give us negative 4. So what I'm doing is I'm grouping the x's together, I'm grouping the y's together, and I'm getting the constant term on the other side. Because what I'm getting ready to do here is complete the square. And we need to complete the square not only on the x's, but also on the y's. So how do we complete the square? Well, we've done this a few times now, so we should be pretty comfortable doing this, I think. So the procedure is you take the middle number, in this case is negative 6, divide it by 2, square it. This is equal to 9. So I'm going to add 9 here, and I'm going to add 9 to the right side of the equation. Do the same thing for the y's. So here we have the number 4. Divide that number by 2 and square it. That is 2 squared, which is 4. So I'm going to add 4 here, and I have to add 4 to the right side of the equation to compensate for that. Now what we can do is we can factor the x's. So that's going to turn into x minus 3 times x minus 3. So that's x minus 3 quantity squared. We can factor the y's. So that's going to be y plus 2 times y plus 2, which is y plus 2 quantity squared. And then on the other side, if you simplify that, you get 9. And so now we can easily see the center of the circle is at positive 3, negative 2, and the radius of the circle is 3. Okay, so now we're going to move on to talk about parabolas. And again, we've already talked about parabolas, but we're going to give a little more information about parabolas this time around. I'm going to talk about the technical definition of a parabola. So it turns out a parabola is the set of all points in a plane that are the same distance from a fixed point and a fixed line. The fixed point is called the focus, and the fixed line is called the directrix. So you all know what a parabola already looks like. And so I took the liberty to go ahead and just bring in a graph of a parabola. You also already know that this point on the parabola is called the vertex. And this so-called focus that we're talking about is a fixed point, and the directrix is a fixed line. And it turns out that this focus is always located on the inside of the parabola, just above the vertex here. And the directrix is a line, a horizontal line in this case, on the other side of that parabola. And the idea behind a parabola is that if you pick a point on the parabola and you find the distance between that point and the focus, and if you find the distance between that point and the directrix, these two distances will always be the same no matter where you are on this parabola. And so that is actually what makes a parabola a special shape. Okay? Now, fortunately, in this class, we don't talk about how to find the focus or how to find the directrix. That's a topic that we save for pre-calculus. But we are going to talk again about the equation of a parabola. And so this is review. You already know from chapter 8, when we talked about quadratic functions, the equation of a parabola is y equals a times the quantity x minus h squared plus k. And in this case, the vertex is the point hk. And you know if a is positive, it opens up. And if a is negative, it opens down. And so this is what I would say is the familiar case, right? This is a parabola with a vertical axis. What does that mean, vertical axis? Well, remember when we talked about parabolas, there was that line called the axis of symmetry, and it would come right down through the middle of the parabola. When your axis of symmetry is vertical, we say that this is a parabola with a vertical axis. So, good news, this should be familiar to you. This is absolutely no different than what we did before. There is another case, though. There is a case where you could have a parabola with a horizontal axis. And so what I'm talking about here is the axis of symmetry would be a horizontal line. And in this case, if the axis of symmetry is horizontal, it means that your parabola opens either to the right or it could even open to the left. So it's all the same stuff except that your parabola doesn't have to open up or down. It could also open to the left or to the right. Now, if it opens to the left or to the right, it is a slightly different equation. The equation is here. It is x equals a times x minus, it's a times y minus k quantity squared plus h. And this will have a vertex of hk. And then the number in front here, the a value, if it's positive, it opens to the right. And if it's negative, it opens to the left. Okay? So let me just put those two equations side by side here, and let's talk about them. So here we have the vertical axis equation, and here we have the horizontal axis equation. You should notice the equations are really similar to each other. In fact, the only difference is two things. Number one, x and y get switched. And number two, h and k also get switched. That's all there is to it. So if you know how to graph parabolas with the vertical axis, graphing a parabola with the horizontal axis is pretty much the same thing. Let's look at some examples. So our first example here, we're going to graph the parabola having the equation y equals negative 2 times x plus 1 quantity squared minus 3. This is going to be a parabola that opens down because a is negative 2. And its vertex is going to occur at x equals negative 1 and y equals negative 3. Now, to graph this, we're going to first go to the vertex. So negative 1, negative 3 is right here. That's our vertex. And it's going to open down from there. Now, again, when you're doing this on your online homework system, if that's how you're doing homework, this is pretty easy to do. All you have to do is graph the vertex, graph another point, and then use the tool to connect them. But if you're doing this on paper, like I'm kind of doing right now, what we need to do is find a couple of other points on this parabola. So I'm going to put my vertex point, which is negative 1, negative 3, right in the middle. And I'm going to plug in x equals 0 and positive 1. And I'm going to plug in x equals negative 2 and negative 3. And so we just have to take these values and plug them into the equation. So I'll just do this mentally with you. If x equals 1, 1 plus 1 is 2, 2 squared is 4, 4 times negative 2 is negative 8, and negative 8 minus 3 is negative 11. So If x is 1, y is negative 11. If x is 0, y will be negative 5. If x is negative 2, y will be negative 5. And if x is negative 3, y will be negative 11. So to graph this, we just have to sketch those points. So 0, negative 5 is here. 1, negative 11 is just at the edge of my graph down here. Negative 2, negative 5 is here. And negative 3, negative 11 is again just at the edge of the graph down there. And so our parabola looks like this. And this should be fairly comfortable because, again, you did this back in chapter 8. So this is pretty much the same thing. All right. Our next example, number 2 here, is a parabola with a horizontal axis. And we can tell because it's x equals a y squared instead of y equals an x squared. That's the main difference. Now, what are the coordinates of the vertex? Well, again, we know we have to take the opposite of negative 2 here, which is positive 2. That is the y coordinate of the vertex. So that goes here. Positive 1 then would be the x coordinate of the vertex. And so what we have here is 1, 2, which is this point. This is our vertex. It is going to open to the right because we have a is positive 3 here. And all we have to do now is get a couple of points. And I'm going to make this really simple in this case. We have x coordinates and y coordinates. We know the vertex occurs at 1, 2. Since you have x equals a function of y, to find points, it's easier to pick a y value to get the x value. So I'm going to pick y equals 3 and y equals 1. And if you plug those in, you will get x equals 4 here, and you will get x equals 4 here. And so that gives us the point 4, 3 and 4, 1. And if we just connect those, you can see that your sideways parabola here kind of looks like this, okay? And that is good enough for what we're trying to do at this point. Let's take a look at one more. So in this one, we want to write the equation in standard form and then graph it. So what we have here is what you would call the general form, and we want to write it in standard form. Okay, so standard form means we want it to look like this. So what do we have to do to write it in standard form? Well, we have to complete the square, right? So let's go through the process. We have x equals, first of all, we're going to factor a negative out. So that gives us y squared plus 4y, leave a space, put the plus 3 on the outside. We're going to take the middle number, which is 4, divide it by 2, and square it. This is 4, so we're going to add 4 here. And we are going to add 4 out here because this negative really makes this 4 a negative 4. So we have to add 4 to cancel that. That's the tricky part. So this is x equals negative quantity y plus 2 squared plus 7. So what's the vertex? Well, the vertex is going to be y equals negative 2 and x equals 7. So now to graph this, we'll go to x equals 7, y equals negative 2, which is down here. And then we'll need to get a couple of points. So again, we have x and y. We know x equals 7, y equals negative 2. And once again, to get points for this one, it's easier to pick a y value to tell you what x is, which is backwards from what we usually do, but it's easier in this case. So I'm going to pick y equals negative 3 and y equals negative 1. And if we plug in y equals negative 3 plus 2 is negative 1. Negative 1 squared is 1. That negative makes it negative 1 again, and plus 7 is equal to 6. And when you plug in negative 1, you will also get 6. And so what we have here are the points 6, -3, and 6, -1. And if you wanted to get a couple of more points, you can. I'll just show you what those points look like. So if y equals 0, for example, we'll get 3. And if y equals -4, we'll also get 3. And so if you wanted to get a couple more points, you can. And then finally, the graph of this parabola is going to look something like this. Okay, so graphing a sideways parabola is not that hard to do. You just have to be careful. I know that's kind of cliche, right? You always have to be careful, of course. But the hardest thing, I think, is just getting used to the x's and y's being switched, because it's just a little bit different and a little bit uncomfortable at first. Okay, so that concludes our discussion about parabolas. The next section is 10.2. In this section, we introduce the concept of what is known to be an ellipse. An ellipse, in short, is this oval-shaped graph that you see here. An ellipse has a definition. Its definition is that it is the set of all points in a plane for which the sum of the distances from two fixed points is a constant. And those fixed points are called foci, or some people call them foci, but that's just the plural of the word focus. So we don't say focuses, okay? Anyway, so the shape turns out to be this oval-shaped thing. You will have a center at some point. You will have a focus here and a focus here, and those two foci are on the longer axis here. So you'll notice that when you have this oval-shaped graph, you will have a sort of longer axis, and you will have a shorter axis. The foci are always on the longer axis. Now, once again, thankfully, we are not going to worry too much about finding the foci in this class. That's a topic for pre-calculus. But the main idea is that if you pick a point on the ellipse, and if you take the distance from that point to one of the foci, and if you take the distance from that point to the other focus, when you add those two distances together, you will always get a constant. You will always get the same thing, no matter what point you pick on the ellipse. That's the key point to make. So if I pick a point over here, the distance to this focus plus the distance to this focus will always be the same. Okay? Now, what does the equation look like? Well, we're not going to derive the equation, but it turns out the equation looks very similar to the equation of a circle. Doesn't this look kind of like the equation of a circle? A little bit, right? So what we have here is x minus h squared over a squared plus y minus k squared over b squared is equal to 1, right? So remember, a circle had this equation. Right? A circle has this equation. And that r is the radius of the circle. Well, this is kind of like a circle, except that it has a radius that is longer on the horizontal axis and shorter on the vertical axis. And that's what these two numbers a and b tell you. Okay? So, for an ellipse, a is always the larger of the two numbers. And if the larger number is below the x's, you're going to get this kind of an ellipse that is longer on the x-axis and shorter on the y-axis. Okay? If that larger number a is below the y's, like in this equation, then the ellipse will be longer on the y-axis and shorter on the x-axis. And again, if this is a little bit confusing right now, don't worry, the examples should clear it all up. So let me talk a little bit more about what I was just saying. So you have your two equations for an ellipse, either this one or this one. And the a and the b here, as I was talking about, refer to the distance from the center out to what we call a vertex. That's our distance A. And the distance from the center out to a co-vertex is our distance B. And so our V1 and V2, those are the vertices. The CV1 and CV2 are called the co-vertices. The vertices are the points that are farther away from the center. The co-vertices are the ones that are closer. And C, of course, is the center. Now, one other thing that I'm just going to mention here is the distance from the vertex here all the way across to the vertex here. That is what we call is the length of the major axis. And the distance from the co-vertex here to the co-vertex here, this is what we call is the length of the minor axis. Okay, but don't worry too much about major axis, minor axis, focus, etc. What we're focusing on in here is just getting the basic graph of the ellipse. And it turns out that it is really, really easy to get that graph. Let's do some examples. All right, so starting with our first example here, I want to graph x squared over 9 plus y squared over 4 is equal to 1. And the first thing I'm going to do this graph is I'm going to rewrite that equation just a little bit to help us understand it. So we can think of this as x squared over 9 is 3 squared. And then y squared over 4 is 2 squared. So in this problem, A is 3, B is 2. The center of this ellipse is the origin. It's at 0, 0. So the center is here. To graph the ellipse, the A and the B tell you how far to go from the center out to the vertices and the co-vertices. Here's how you do it. The number 3 comes from 9, which was below the x's. So what that means is from your center, you're going to count 3 units along the x-axis to the right and 3 units along the x-axis to the left. So we go 3 units to the right, 3 units to the left, and these are our vertices. And then the co-vertices are found by going 2 units above and below the center. So we have a point here, and we have a point here. This is co-vertex 1 and co-vertex 2. And then to graph the ellipse, all we have to do is connect those points. And when you make that connection, it's basically going to look like an oval or a compressed circle, if you will. That is literally all there is to it. Okay? It's really that simple. Let's take a look at our second example. So to graph this one, what I'm going to do here is I'm going to rewrite this. I'm going to think of 9 as being 3 squared and 16 as being 4 squared. So if we rewrite this equation, we get this. Oops, let's rewrite that, I said. So for this problem, A is 4, right? Remember, A is always the larger number, and B is 3, and the center of this ellipse is at x equals positive 1, y equals negative 2. So first you have to go to the center, positive 1, negative 2, and then the A and the B will tell you how far to go from the center, left and right, and up and down. In this case, A is 4, but that 4 came from the 16, which was below the y variable. So what that means is that from the center, we have to count 4 units up and 4 units down. So when we do that, we get a point here, that's a vertex, and we get a point here, that's another vertex. And then B equals 3, well, that number came from the 9, which was below the x's. So that means from the center, we're going to go 3 units in the x direction. So that would be left and right. So 3 units left and right. And that gives us a co-vertex 1 and co-vertex 2. And then the ellipse itself, you just connect these points together. Okay, so again, I feel like it's really simple to graph an ellipse. Pretty straightforward process. Let's look at one more. So for our last example here, what we need to do is we need to first write the equation in the form of what we usually have for an ellipse. And what we usually have is that the equation has to be equal to 1. So the first thing I need to do here is I need to divide both sides of the equation by 9, because I'm looking to make 1 here. So if we do that, we get x squared, right? 9 over 9 cancels, so I'll write x squared over 1, plus y squared over 9. 9 is 3 squared, and this is equal to 1. And 1 is the same as 1 squared. So for this problem, we have a equals 3, b equals 1. This is an ellipse. Center is at the origin. Since 1 is the number below the x, we're going to go 1 unit to the right and 1 unit to the left. And since 3 is the number below the y, we're going to go 3 units up and 3 units down. And then we simply connect the dots. So graphing an ellipse is pretty straightforward, simple stuff. All right, finally, we'll look at section 10.3. We're going to talk about a graph called the hyperbola. So we'll start with the definition. A hyperbola is the set of all points in a plane for which the difference of the distances between two fixed points is a constant. And again, those two fixed points are called foci or foci, either way. It's the plural of focus. It turns out that a hyperbola is a very different graph from everything that we've talked about before. What you get is some sort of a U-shaped kind of graph going one way and another one that kind of is a mirror image going the other way. Now it does have a center right here in the middle. This point here is called a vertex. This point here is a vertex. And those two fixed points that we call foci would be here and here. I guess if you have to make a comparison, it kind of resembles a parabola. But it's not a parabola. It's very different from a parabola. So just starting with the definition, if I pick a point on this so-called hyperbola, and if I take the distance from that point to one focus, and I take the distance from that point to the other focus, those two distances, when you subtract them, is always a constant number. It's always the same, no matter what point you pick on either of the two graphs there. So we're not going to worry too much about the focus. We're not going to worry about some of this other stuff. What we just want to focus on is how do you get the graph from the equation? Now, one positive thing is the equation for a hyperbola is very similar to the equation of an ellipse. The only difference is you have a minus sign here instead of a plus sign. That's the only difference, okay? Now, the other thing is you can have a hyperbola that opens to the left and to the right. That would be this equation, okay? So this equation would be a hyperbola opening left and right. And you can also have a hyperbola opening up and down. And we'll do examples of both of these. Before we look at examples, there's one more thing we have to talk about regarding this hyperbola. So I've zoomed out a little bit on what this hyperbola looks like. So here's our hyperbola here, this blue graph, and we have a hyperbola here. And you'll notice that I've put in a couple of lines in the graph. And these lines are called asymptotes. And when you're graphing a hyperbola, you have to have these asymptotes in here because as this graph moves outward, what it does is it gets closer and closer to that asymptote without ever touching it. Okay, so it gets closer there, and it also gets closer over here, and it gets closer out here, and you can see it gets closer out here. So you have to have these asymptotes in place if you're going to graph the hyperbola. Otherwise, if you don't have these lines, you might just graph something like this, right? I mean, how do you know what it looks like if you don't have those lines to guide the graph, okay? So let's talk about how to graph hyperbolas. And again, I'm going to give you a very functional method for doing this. All right, here we go. The first thing you do when you graph a hyperbola is the same thing that you do when you graph an ellipse. You have to identify the center. And for this first example here, the center is 0, 0. So we'll go ahead and put that center in there. Then, just like you did with an ellipse, you're going to think about the number 4 as 2 squared. You're going to think about the number 9 as 3 squared. And what that tells you is how far to go to the left and to the right of your center. So again, because the 2 here is below x, means I'm going to go 2 units to the right and 2 units to the left. And because the 3 here is below the y, I'm going to go 3 units up and 3 units down. Now, if this is an ellipse, what you do, of course, is you draw your oval and you're done. But this is not an ellipse. This is a hyperbola because we have a minus sign here. So the next thing you do is you create a rectangle, a dotted rectangle, using those 4 points that we just got. So there's our dotted rectangle. Now, we don't really care about the rectangle. What we care about are the diagonals of that rectangle. So a diagonal for a rectangle is a line that goes from one corner through the center to the opposite corner. But we're actually going to draw infinite diagonals, and so we're going to extend that diagonal in both directions. So if I draw that diagonal very carefully, I get this and this. And that diagonal, that is one of your asymptotes. And we do the same thing for the other one. And the same thing down here. Now we have everything in place to guide our graph. So the only question is, does your hyperbola open left and right, or does it open up and down? Simple answer is, since x is first, it opens along the x-axis. So it will open to the left and it will open to the right. So now we just have to sketch the graph. The vertex of the parabola is always on the box. So we have a vertex here, that's V1. And when you sketch the graph, you're just going to sketch it as it gets closer and closer to the asymptotes. And that's our second vertex. Okay, so that is what the graph looks like. So again, you have to graph the center. You have to go the distance to the left and right, up and down, create the box. The box is there so that you can draw these asymptotes. Once you draw the asymptotes, you then determine if it opens left or right, and then you sketch the graph. And the key, again, is that when you sketch the graph, this graph should be getting closer and closer to this line, but it never touches it, though. And the same thing over here, closer and closer without touching. And same thing down here, and the same thing down here. Okay, that's basically how it's done. Okay, let's look at another example. So again, for this one, first thing we have to do is we have to identify the center. So center is going to have a y-coordinate of -4 and an x-coordinate of +3. So y-coordinate -4, x-coordinate +3. So that would be this point right here. Now, from that point, again, that's our center. From that point, we are going to move 16, remember, is really 4 squared. So we're going to move 4 units up and 4 units down. Now, why are we moving up and down instead of left and right? Well, again, because that 16 is below the y variable, and the y variable goes vertical. So we go 4 units up and 4 units down. The 25 here is really 5 squared, and that's under our x variable. So we are going to go 5 units to the right and 5 units to the left. And then we create our box. Which looks like this. And the box is really only there to create our asymptotes, which look like this. And I can see that my graph is not quite big enough for what I really want to do here, but we'll make it work. Okay, we do the same thing over here. And then now it's time to actually graph the hyperbola. Now, because the y variable is first, this is going to be a hyperbola that opens up and opens down. And as you're opening up here, the point that's on the box there, that's your vertex. So we have a vertex here, and then it opens this way. Whoop, that's terrible. Let me regraph that. Okay, let's not be too sloppy. So we have our asymptote there, and then it's going to move out and closer like this. And same thing down below. We have a vertex down here, and it's going to move out this way and out this way. Okay? And so the black graph, that's actually the hyperbola. Okay, that's actually the graph that we're graphing. All the other stuff, the dotted stuff, that's not actually part of the hyperbola, but you need those to graph the shape correctly. All right? Let's look at one more. Okay, so for this one, again, we have to find our center first. Center here is x equals 0, y equals -2. So 0, -2 is right there. There's the center. The number below x is 9, which is really 3 squared. So we're going to go from the center 3 units to the right, 3 units to the left. The number below the y's is 16, which is really 4 squared. So we go up 4, down 4. And then again, once you have these 4 points, you just make the box. And the box is there so you can draw the asymptotes. And again, you don't have to make your asymptotes dotted, but you really should. And I'm trying to distinguish between what is the graph that you're actually graphing and what are the things that just help you guide the graph. So there's our asymptotes. And again, because x is first now, this is going to be a hyperbola opening to the left and to the right. And so we'll have a vertex here, opening this way. And we'll have a vertex here, opening this way. And that is all there is to it. All right, so I know this is a lot. I know it's new stuff, but actually once you get the hang of graphing these 4 types of graphs, circles, parabolas, ellipses, and hyperbolas, it's not that bad. You just really got to get practice.